One-dimensional harmonic oscillator. Part A. Show by direct substitution in the Schrödinger equation for the one-dimensional harmonic oscillator that the wave function psi1 of x is equal to a1x exponential minus alpha square x squared over 2, where alpha square is mw over h bar, is a solution with energy corresponding to n equals 1 in harmonic oscillator energy levels n plus 1 half h bar omega. N plus 1 half parentheses h bar omega. So let's write down Schrödinger's equation for one-dimensional harmonic oscillator. It is minus h bar squared divided by 2m second derivative of the wave function d square psi dx square plus the potential term 1 over 2 m omega square x squared. This is basically 1 over 2 spring constant x squared. Psi is equal to energy times psi. So that's the Schrödinger's equation that this wave function has to satisfy. So you can see that I need the second derivative of this wave function. So let me rewrite the wave function here. Psi1 of x is equal to a1x exponential minus alpha squared x squared divided by 2. So let's take the first derivative. What is d psi1 dx? We're going to use the product rule. First, take the derivative of x, which is 1. So this is a1 times the exponential. That's the first term. a1 times the exponential. And then take the derivative of this one, which is minus 2 alpha square x over 2. So minus alpha square x multiplied with x gives us minus alpha square x squared. So minus a1 alpha square x squared times the exponential term. So that's the first derivative. Now I need the second derivative. D squared psi1 dx squared. So I look at the first derivative. I see that the first term has the exponential. So I will have minus 2 alpha square x over 2 minus alpha square x multiplied with a1 minus a1 alpha squared x times the exponential. The second term, first I take the derivative of alpha square x squared, which is 2 alpha square x. So I will have minus 2 a1 alpha square x times the exponential. Then I take the derivative of inside, which is minus 2 alpha square x over 2. So minus minus, this will become a plus. So I will have plus a1 alpha to the fourth power x cubed times the exponential. So that's the second derivative. Now we're going to substitute this second derivative into Schrödinger's equation. So we will have minus h bar squared divided by 2m multiplied by the second derivative of the wave function minus a1 alpha square x exponential minus 2 a1 alpha square x times the exponential. And then I have plus a1 alpha to the fourth power x cubed times the exponential. Then I have the potential term plus 1 over 2 m omega squared. So let's continue down here. So plus 1 over 2 m omega square x square times a1 x exponential, that's psi 1, that's equal to energy times psi 1, E1 times A1 x and the exponential minus alpha square x squared over 2. Now you can see that exponential terms will disappear. And then I have x is disappearing, so this x will get rid of this x. This will make it x squared. This will get rid of this x, and it will get rid of this x. And also a1's disappear. So let's see what we're left with. We have the first term, alpha square h bar square over 2m, minus minus becomes plus. So we have alpha square h bar square over 2m. And then the second term, minus minus plus 2 alpha square h bar square over 2m plus 2 alpha square h bar square divided by 2m. Then we have this term plus minus, so it's going to be minus alpha to the fourth power h bar squared over 2m x squared, and then I have plus 1 over 2 m omega squared x squared is equal to E1. So you can see that we can substitute for alpha square mw over h bar, which was given in the problem statement. So here I substitute mw over h bar, so I will obtain mw h bar divided by 2m, because it's over h bar squared becomes h bar, and here I have the cancellation of these 2's, and this is going to give me mw h bar over m plus mw h bar over m. Then here I have minus m square w square over h bar square, so m square w square divided by 2m x squared plus 1 over 2m omega squared x squared. That's equal to E1. Now you can see these m's cancel, and here I have plus 1 over 2m omega squared x squared minus 1 over 2m omega squared x squared. So they cancel, and I find that the energy here is 3 over 2 h bar omega. So E1 turns out to be 3 over 2 h bar omega, which corresponds to n plus 1/2 h bar omega, where n is equal to 1. So indeed, I find that the given wave function describes the first excited state, n equals to 1, solution of the one-dimensional harmonic oscillator. So first I write Schrödinger's equation, minus h bar square over 2m, second derivative of the wave function with respect to x. This is a momentum operator squared divided by 2m applied to the wave function, and h bar over j d dx is the momentum operator, j is square root of minus 1, plus the potential times psi, 1/2 m omega square x squared times psi is equal to energy times psi. So Hamiltonian applied to psi is energy times psi. So I take the first derivative here and then the second derivative substituted into Schrödinger's equation, and I realize that these two terms cancel out if I substitute alpha squared equals m omega over h bar, and indeed the corresponding energy is 3 over 2 h bar omega, which is n equals to 1 solution for the energy levels of the one-dimensional harmonic oscillator.